Okay. I'll get started. As I think all of you are aware, that string theory, of course, has given itself a pretty ambitious goal, and this goal of this school at some point, at some level, reflects that ambition of starting with physics or thinking about the deeper structures of what combines quantum field theory and quantum gravity, which is what led to string theory, supersymmetry, 10 and 11 dimensions. But of course, a big part of the motivation really comes from particle physics, that we would like to understand the deeper questions about particle physics. And again, yesterday you've seen the standard model, at least summarized on the blackboard, which indeed describes with remarkable success the phenomena that you can see in laboratories. But of course, we want to learn more about it, and string theory is one of the ways of organizing our thinking about it. But clearly, this theory has most of its rigid structure in thinking about aspects of Planck scale physics, and there's quite a bit of freedom in going from the high scale of the Planck scale to the scale where the new particle physics will take place, the TeV scale. And there are many ways of getting lost in going from here to there, because it's a long road. And yesterday it was beautifully explained how grand unification is, at least it's one, and supersymmetry combined give one way of, at least of constraining our thinking in going from here up there. But even so, not only is the road from here to there long, even string theory itself has many possibilities, and even if you are sufficiently aware of all the possibilities, it's still easy to get lost in essentially the landscape of possibilities. And so what I'll try to do in this hour and a half is to give a little bit of a roadmap, at least my personal roadmap, and how I'm trying to, in my own thinking at least, separate the issues and how at what point do you make a choice if you start thinking about how to apply string theory to particle phenomenology, or what kind of lessons in general does string theory suggest about particle phenomenology. So it's more, I'll be taking a bit of a aerial view, so I will not go too much into detail, but sometimes I will, of course, to just illustrate more precisely what's going on. But again, the main point being that where string theory is really sort of trying to address the question of quantum gravity, it comes with one particular issue, namely that it doesn't have any, essentially it starts with 0 parameters. We just had M theory on the blackboard, the 11-dimensional supergravity Lagrangian doesn't have any parameters. And therefore, in order to get 4-dimensional physics, which does have parameters, which are the coupling constants and the parameters in the standard model, all those parameters would have to be derived from some principle from this more unique theory. And that principle, actually, in the end, is really going to be dynamics. It's really, the question is that if we have 4D quantum field theory, it follows from string theory, but what you would have to do here is you would have to compactify. And of course, we're interested in the 4D quantum field theories that might look like nature, but there are many ways of doing this. And the key point that I just mentioned is that coupling constants they are going to be determined dynamically. So you have to say, okay, well, you have to provide some kind of mechanism to say, well, I'm going to look at a certain solution to this unique theory that will have certain properties, but those properties will have to be determined by some potential that you might want to introduce. So the connection between this compactification and determining the coupling constant is an important issue that one at some level would have to deal with, which is known as moduli stabilization. So it's something that at least one needs to address. And then even if one has a way of thinking about this issue, there's going to be a whole range of possibilities, which we call the landscape of possible string compactifications. And this is another issue that you have to sort of come to grips with if you want to do string phenomenology. Now, then there are other practical questions. If we want to get a realistic quantum field theory, then practically at least, you want to get the main features of the standard model. Let me be very global here. At least you want to have gauge symmetry. And another important feature of the matter of the standard model is you want to get chiral matter. And not only do you need to choose how you're going to get this matter out of string theory, and there turn out to be indeed different ways of doing that, you also want to know or choose for yourself which gauge symmetry and which chiral matter you like best. This is, of course, a choice that comes from the phenomenological end, sort of from a quantum field theory perspective, perhaps, whereas this question has to do with, okay, well, how am I going to organize degrees of freedom in string theory in order to get these particular ingredients? So those are two important questions. Let me call this question 1, and the which question 2. And maybe first about question 2. There are, of course, many theories about beyond the standard model particle physics, but I think it's fair to say let's divide them up right now into two basic categories. One would be, let me introduce, keep SUSY in there, indeed the SUSY grand unified theories, where one takes all the evidence that points to a more unified high energy perspective when it comes to the gauge interactions. That's one road one could take. Or one could be a little bit more skeptical about the evidence for grand unification, or maybe one is just trying to be more practical and more modest in terms of the assumptions that one makes that go beyond what we've actually seen. And then you would maybe view things more from the bottom up and just look at the standard model as a goal of how to make the standard model within string theory, or looking at ways in which the standard model can arise within string theory. So this is a little bit more top-down. That's a bit more bottom-up. Another issue, which I'll call actually issue 3, which will be, of course, important, which has to do with making a choice of SUSY breaking, of how does supersymmetry get broken. This will be discussed a bit more next week in this school. I'll maybe say a few things about this, but not too much today. Now, with respect to question 1, there's sort of different paradigms, and roughly I could say, let me call it 2 paradigms, although it's a bit of a heavy word for the whole thing. One, I would say, is global, and the other one is local. And I'll give examples of both. We just had the discussion of the heterotic string, and indeed, I would say the old paradigm was that chiral matter and gauge symmetry would indeed be present ideally in the 10-dimensional theory, which was then the heterotic string. But then, if you want to go to 4 dimensions, you want to clearly then compactify, and then the properties of the 4-dimensional theory would depend on the properties, the global properties of that particular compactification. And one other way of looking at the change in thinking that took place in the mid-90s, where up to that point it seemed that the phenomenological approaches were all starting from the heterotic string, that afterwards the arguments that were given against the other types of string theories, which initially were non-chiral in 10 dimensions. The 11-dimensional supergravity was non-chiral. The 2A and 2B did not have chiral matter and did not have gauge symmetry. Later we started understanding that if you take those theories and are a little bit more creative in the kind of geometries, possibly singular geometries, or in the kind of objects that you introduce in those theories, which are D-branes, then there are actually many other ways in which those other theories, which initially do not have those ingredients in the higher dimensional perspective, do get those ingredients upon compactification to 4 dimensions. But a common theme there is that then the matter often arises by local, is localized within the extra dimensions. So this is an important distinction. So as my first little roadmap, let me indeed then divide this blackboard into 4, depending on whether indeed you want to take the grand unified perspective or take a standard model type perspective, or whether you want to do things globally, meaning that, and I'll be more precise about what I mean there, where you really try to think more globally about the properties of your compactification, or you start to imagine that things can be studied by just thinking locally within the extra dimensions. And this local perspective, as we will see, will have a somewhat more direct correspondence with just using 4D quantum field theory. So you can put yourself in these 4 corners. And I would say that mostly the heterotic string, at least traditionally, was in this particular corner here. And this I would call top-down perspective. But there's also a local perspective where, for example, you would take D-branes in type 2A or type 2B theory, and you can use those D-branes as your ingredients and just look at what they locally represent as a way of building quantum field theories that look realistic. And this would then be, you could call a bottom-up approach. And Luis Ibañez, I think, will say much more about this particular D-brane approach. Now, even with D-branes in type 2B, you could still look at things a bit more globally and look at the interaction or between the D-branes and the geometry, the Calabi-Yau geometry in which these D-branes are embedded. So this particular approach has also sort of a more global perspective. For a long time, it turned out actually that the ingredients that we could use to make local constructions of chiral matter were a bit less adept at describing things from the grand unified perspective. But more recently, I think people have definitely made progress by thinking about F theory. And I would say M theory sort of sits a little bit in the middle here between the global and the local. So this is roughly a bit of a roadmap. That 2B string theory at least has mostly been developed so far as a way of using branes to represent Lagrangians that look more like the standard model, whereas the grand unified perspective took more the heterotic string route. More recently, the F theory route and M theory has been applied from this perspective as well. So this is a very rough division. Now, I mentioned F theory, which I will say a little bit more about later, either today or next week, and next week we'll have more lectures about it. But if this is the whole landscape or the picture of string theory, this picture often has been shown, where you have these different corners. And indeed, the 2A string theory might sit here, 2B string theory might sit here, type 1 string theory might sit here, and the heterotic string here, and M theory sits then there. And what one means by this particular picture is the following, is that by now, in part mostly by these dualities that were just mentioned this morning, we kind of have ways of reorganizing degrees of freedom in each of these corners and essentially establishing by just performing tests, I would say, that those degrees of freedom, indeed, if one would start cranking up the coupling and that the weakly coupled description in one case would become more strongly coupled and then eventually connects with another weakly coupled description, which we would actually give a different name, where the degrees of freedom have been reorganized. So these corners here is what you could call weakly coupled string theory. But there's this whole thing in the middle there where none of those descriptions that we actually have currently available would actually be applicable, and everything would be strongly coupled. And if you are a pessimist, then you could say, well, this means that again, there's a lot of string theory which is quite useless and might not be, and we might live there in the middle, and then we're stuck. However, we know that the standard model and the particle physics that we have is actually a weakly coupled theory. And one would have to be very sort of cynical to assume that that weakly coupled theory does not have a correspondence with a particular weakly coupled expansion from one of these corners. But you would have to still, if you do phenomenology, you actually have to choose a particular perspective. And anyway, you have to make it. And that puts you on a particular trajectory. But as I said, besides choosing those particular points, there's another kind of choice you would have to make, is in which corner of these, in which quadrant of this thing you would put yourself. Okay, so this is very, very global, so let me get a little bit more specific and talk about the old point of view of the hydraulic string. And I'll be very brief there because mostly we'll be talking in the next 2 weeks about things that are somewhat more recent and that take a different, somewhat different perspective. But several of the ingredients of the hydraulic string, of course, are quite universal. Yes?
Where would you put F theory on that?
Oh, yeah. Okay, thank you. Thank you for, I actually wanted to do that. So F theory actually is simply a reformulation of 2B string theory. Just at the end of the previous hour, John wrote down this field tau, which is the dilaton, in combination with the axion field. And what F theory is, it's nothing else than a range of solutions of 2B string theory where the dilaton is not constant. And that's what F theory is. But it gives opportunities by allowing the dilaton to be not constant. And actually, it turns out that if you take a 7 brane in 2B string theory, that it sort of naturally leads to this tau parameter to have non-trivial behavior. And by being creative with how you do things with that dilaton, you have other ways of making chiral matter in F theory that you would not immediately see from the 2B string theory perspective. And that allows one to actually make grand unified gauge groups that one would not be able to make purely by considering perturbative D-branes. Although I'll not say too much about it, it turns out, and there might actually be a deeper lesson in all of this, that if you take D-branes, it's very hard to make grand unified groups. SO10, in principle, you can make SO10 from a D-brane. It was mentioned that D-branes can have SO2 and gauge groups. But to make the 16, the representation 16 of SO10, that's already a harder thing to do. And morally speaking, actually, SO10 with the 16 is a little bit like making an exceptional gauge group. It sort of has some connection with E6. And as soon as you make exceptional gauge groups, which are not SO or UN gauge groups, then D-branes essentially don't allow you to do this. The rules of the Chan-Payton factors, the way of stacking branes, does not allow you to go in that direction. And there might be an interesting lesson in the fact that those exceptional groups enter more naturally in the grand unified setting, whereas sort of the low energy perspective, that D-branes seem more adequate for describing that. SU5 can be described by brane constructions and even with the representations that would be useful for a grand unified setting. It turns out that in that case there's a bit more of a technical shortcoming of the D-brane construction, namely that the Yukawa coupling that eventually becomes the top, sets the top mass, would not be classically allowed in the string theory. It would have to come from some instanton effect or so, which actually would suggest that the top mass should have been the lightest particle in those kind of models, which clearly, the top quark, which is clearly not a good starting point. So roughly speaking, one could say the separation between these two approaches is indeed, do you use deep brains or do you use something else? Now, so starting in '84, very quickly again after the realization that SO32 and E8 times E8 string theories were unique ways of getting started with chiral theories in 10 dimensions, it was realized that in order to go to 4 dimensions in a way that preserves n=1 supersymmetry, there's a rather unique type of geometries that will do this for you. The requirement that you would have for that geometry would be that the n=1 supersymmetry in 10 dimensions survives as an n=1 supersymmetry in 4 dimensions, which means that the supersymmetry, which is a 10-dimensional spinor, you would have to decompose it into a 4-dimensional spinor times the 6-dimensional spinor of the internal manifold, which is a 6-dimensional Calabi-Yau manifold. And that internal spinor essentially would have to be a covariantly constant spinor. It would have to be a constant. And if you write down the geometric condition that a certain manifold, a complex manifold, would have a covariantly constant spinor, you'll find geometric conditions that essentially mean that that particular manifold has to be a Calabi-Yau manifold. So this was good. At least it gave us a rather concrete class of manifolds that we wanted to look at. Geometrically speaking, you could say one way of classifying what a Calabi-Yau manifold is it's one that satisfies the Einstein equations in terms of that it solves the equations of motion, but also it has SU3 holonomy, and the SU3 holonomy essentially means that the way in which coordinates are patched together along that manifold indeed preserve this constant, the existence of this covariantly constant spinor. Now, whereas perhaps initially people were a bit optimistic that the space of Calabi-Yau manifolds would not be that big, that the number of possibilities of compactifying a heterostring could perhaps be small, it turns out that there's a huge space. So let me say a little bit about that space, because it's also the one that's relevant for the other string theories as well. Now, a Calabi-Yau has all kinds of properties. I'm not going to be very complete about this, but one object that turns out to be useful just to be discussing, on a Calabi-Yau you can have a holomorphic 3,0 form, and we'll call it omega, and it's just a property of that particular manifold, and it's a useful way of organizing things a little bit. Now, if I would have the metric on a Calabi-Yau, it would actually be a Kähler manifold, so I can use complex coordinates. Then a given Calabi-Yau can still have all kinds of shapes, and it can have sizes. So I can change the size of a Calabi-Yau, and we call the parameters that change the size of the Calabi-Yau Kähler moduli. And essentially what it means is that you take your metric, and this is a 1,1 form, one component here, one component there. And so for every 1,1 form on your manifold, you can change your metric and the size of these of various components of your Calabi-Yau manifold. And the number of 1,1 forms, which is the dimension, and these actually have to be holomorphic or harmonic 1,1 forms, but it's the 1,1 homology class, and the dimension of that thing will tell you how many of those parameters you have. And it depends on your Calabi-Yau, it depends on the topology of your Calabi-Yau, how many of those things you have. The metric also will tell you something about the shape. And for example, I could start with my metric, and I can deform it a little bit. and in a way that deforms what we call the complex structure. So what that means is that the distinction between holomorphic and anti-holomorphic coordinates changes by that complex structure deformation, and very schematically, there could be an object A bar A, G, how does it work? A bar, yes, B, whatever. Let me do it like this. Yeah, so this thing actually, right, so if I change my metric, which initially only connects the anti-holomorphic and the holomorphic coordinates in a way that it actually has a component that connects the holomorphic coordinates with itself, I can write it like that. So this would be a change in the complex structure, which is a change in the shape of the manifold. This here is a 1, minus 1 form because one index is down and one index is up. And what I can do, I can multiply that 1, minus 1 form with the 3, 0 form, actually with the 0, 3 form, and get so-called 1, 2 forms. And the 1, 2 forms indeed are the way in which typically one would classify the infinitesimal deformations, the complex structure deformations of the Calabi-Yau. So the number of shape deformations is connected with the dimension of H1, 2. And again, there can be many shape deformations for a given Calabi-Yau. Now, if the world had been supersymmetric, and if in our world we would have found many massless scalars, then this would not have been a problem. Because then we would say, okay, well, let's count the number of massless scalars. Because each of these deformations of your manifold would actually correspond to what we call moduli fields in 4 dimensions. They are scalar degrees of freedom once you look at it from a 4-dimensional perspective, and therefore the let me go here. The task that we have in order to get a realistic theory would be actually to get rid of these kind of deformations and to actually pick a particular value. But as I said earlier, picking that particular value really requires dynamics. The parameters of these compactifications have to be determined dynamically. They have, these moduli would have to be stabilized. Okay, let me, before I actually start discussing how that happens, let me give you a somewhat convenient way of parameterizing these complex structure deformations. So the shape deformations are also called complex structure deformations. So if I have my Calabi-Yau, as we see here, the harmonic 1, 2 forms are in one correspondence with these shape deformations. So, and if I have forms, then I also have corresponding cycles. So it turns out that a Calabi-Yau has a bunch of cycles, which I can call A cycles, and these are 3 cycles. And although this is a 6-dimensional manifold, you can view it a little bit from this perspective, that for every cycle there's what we call a dual cycle that will have precisely one intersection with that particular cycle. So there are an equal number of B cycles, and the number of A cycles is actually equal to the dimension of this 3 cohomology here, at least the ones that I want to look at. And one way of parameterizing the complex structures would be to take that particular 3 form and to introduce a bunch of coordinates zi, because I could have a bunch of these cycles and a bunch of those cycles, and take my 3 form and integrate it over that 3 cycle and get a number, and that's my coordinate that parameterizes the shape of that thing. Now, if I take the integral over the B cycle of this 3 form, I get some other number, but that number is not an independent coordinate anymore. You can re-express it into those functions. And one often introduces some kind of superpotential or a prepotential and writes it like this. There's some function f of z where it turns out that those periods can be written like that. Now, those z's, again, would be scalar fields in 4 dimensions, so we would need to have a potential for that would fix those things. Now, the idea that was first worked out in more detail by Giddings, Kashrut, Polchinski, but there were earlier hints of this, that you can actually use fields that are other fields that are present in string theory as a way of providing that potential. And there are, in particular, these form fields which have been mentioned several times that couple to d-branes, and you could introduce those fluxes for those Riemann-Roch fields. And you can also actually introduce d-branes as a way of, these are discrete parameters that one can introduce, and those discrete parameters can be used to give a potential on this space of continuous parameters, z, that are parameterized by the z's. So let me take that particular perspective. So in the case of 2B string theory, but there's a similar story that holds for 2A, there's a 3-form potential field strength, which comes from differentiating the NS 2-form B and F3 as, are we calling it A2? I'm calling it C2. It's the Riemann-Roch field. And very often one actually combines this into a thing like this, G3 being F3 plus this tau, which was introduced at the end of the last lecture, which involves the dilaton times 3. This is just a linear combination of those two things. And what's actually special about those things is that if I take these three-form fields, and I integrate them over a cycle, that I should get an integer. So this could be an integer ni, or the integral of f3 over some cycle ai could be some other integer. Let me call it n tilde I, whatever. Okay, so you can choose a lot of numbers by having these fluxes on your manifold. And actually, it turns out you can choose quite a few of them. It turns out that one cannot put an arbitrarily large flux on a Calabi-Yau manifold, but they can still get pretty big, so that the number of possibilities that you can put here typically could go into the 10 to the 500. So there are discrete parameters you can choose. But the nice thing about doing this is that the kinetic energy, the energy that's contained in those Riemann-Roch fluxes, provides a potential on the space of these deformations. Yes?
When you define the fluxes, don't get very large
Yeah, so that's precisely the point. The fact that the equations of motion have to be satisfied is precisely what leads to a potential. So let me explain that point. Because indeed there are two perspectives. You can say, well, I'm turning on the field, and then but I have to do it in a way that satisfies the equation of motion. Or you can take another perspective where you say, well, no one forbids me to turn on an integer. At least I can just choose that integer. And then I keep that integer fixed. And then in order to satisfy the equations of motion for my flux field, I'm going to modify my geometry rather than letting the flux match the geometry. You let the geometry match the flux. And that's an important insight, actually. So very schematically, if you have a form field, you get just a Maxwell type or generalized Maxwell type. And maybe there's an im tau here. So you would have some contribution to the energy that's contained in this kind of compactification coming from those fluxes. And it turns out that you can write this in a somewhat clever way, where you take that combination G3 over here, and if you write it like that, then you'll see that the equation of motion, which would minimize the action, would actually be satisfied, and you could have a plus or minus sign here and a plus or minus sign there, but if this particular combination would be equal to 0. So G3, the Hodge star of G3 would be I times minus I times G3. We call this imaginary anti-self-dual. So this particular condition minimizes the energy, but since it involves the Hodge star over here, it actually depends on the choice of geometry on your complex structure of your Calabi-Yau manifold. So again, one could try to say, well, I have to satisfy this equation and choose my fluxes appropriately, or I can choose my fluxes and adjust my geometry so that this condition is satisfied. To make this a little bit more explicit, so this fixes the Zi's. To make it a little bit more explicit, it turns out that you can write down a superpotential such that this term here, let's call that the potential V that we want to minimize, so that V is the d I of W squared, where this I, again, where this superpotential is a function of these Zi's, the ones that are head over there. And it turns out that the form of the superpotential is actually quite simple. You integrate over your Calabi-Yau manifold this free-form times the three-form field strength G. You can show that if you take this particular superpotential and you compute the potential this way, it actually reduces to that. Now, but this particular superpotential, if I would expand it in terms of the Zi's, then it turns out you can use this integral over the Calabi-Yau. You can actually separate it out because these are both harmonic forms into integrals over 3 cycles. So it would look like something like n plus, it would have these kind of things in it, plus some other fluxes m, I, something like that. It would be a bunch of integers times certain functions of the Zi's. Those integers are fixed, but what I'm instructed now to do is to take the minimize this thing, because that's the way in which I would minimize the potential by requiring that the superpotential is minimized. And this particular condition that the superpotential is minimized implies that particular condition that the whole thing is imaginary self-dual. So that has, if you choose your fluxes appropriately, has a unique solutions for the Zi, and this is one way of getting rid of the shape of your Calabi-Yau. Now, so this is very good news, actually, because indeed it replaces a problem that we had, namely massless fields in the spectrum, by at least something that is less of a problem, namely we have a bunch of solutions, namely we can choose those integers, but for given integers, there's a unique shape of the geometry that we're talking about. Are there more questions about this? Which moduli space are we talking about now? The complex structure moduli space? No, so here I'm doing type 2b. For type 2a, one would not have 3-form fluxes, but you would have a combination of 2 4-form fluxes. There's still a 3-form flux, and a similar game can be played. Okay. Okay. So you're talking. Okay. Let me say a few things about this. So so the question is, are we assuming that we're already sort of in a corner of this diagram over here? Probably we are at some level, but things can go pretty generally, I think. So when Calabi-Yau manifolds were introduced as a way of compactifying string theory, there was already obviously a bit of a conceptual jump that was made, because earlier we've been discussing really how to quantize string theory in flat space. And you could immediately say, well, how do you know that string theory actually makes sense on a curved space like a Calabi-Yau space? Now, people have actually constructed conformal field theories which really allow you to consider string propagation in spaces that at least you could argue are very small versions of Calabi-Yau. So string corrections, alpha prime corrections, at least in certain cases, have been put under control where this whole story actually, for example, this particular structure here, which is connected to what's called special geometry, which is the space of deformations of Calabi-Yau, has direct correspondence with the space of conformal field theories, supersymmetric, that preserve supersymmetry. So there's quite a bit of evidence that this is the right geometry that also extends not only to large volume cases and small volume. And there are other kinds of techniques that people have developed to look at small volume Calabi-Yaus. So a lot of this story in that respect continues. But it's a valid question, because as you said, there might be evidence in some cases where you could actually continuously go from one Calabi-Yau with different number of cycles to another Calabi-Yau, so you can change the number of cycles if you want. But once, by the way, so this is a continuous deformation of the ZIs. But once I have fixed the ZIs, then of course I know where I am. And then you can just verify whether your potential is minimized in the range of approximations where you can trust what you've done. If the value of the minimum is at the right spot, you know what you've done. No, but you can check, in a specific case, one can check where the minimum lies. And then indeed one finds, for example, that this minimum sometimes lies in corners where you did not perhaps expect it. And I'll actually mention one example of this. It turns out that indeed this Calabi-Yau, whereas you might think that it's always smooth, actually typically has some kind of a few conifold type singularities. It has a bunch of singularities in it. And actually singularities are not bad, they're going to be good. At least that's one of the themes in the remainder of what I'll talk about. Other questions? Yes?
Yeah, I'm confused about how you wrote down the superpotential study.
Why this is a superpotential? So read about it, think about it this way. So your Calabi-Yau is just a bunch of cycles. I'm not specifying the geometry, I'm just specifying the topology for now first. And I give myself a bunch of integers, which are fluxes, okay? Now choose the geometry on your Calabi-Yau, and then then this will correspond to a particular field on your Calabi-Yau. You put that here, and you have your 3-form on your Calabi-Yau, and then you do this integral. Now it turns out that this integral here indeed is a function of these numbers Zi. And that's the sense in which it is a superpotential. The Zi's are chiral multiplets, so this is a holomorphic function of certain fields that would have been fields in 4 dimensions if it were not for the fact that eventually this potential will give them a mass. So I view this thing as a function of the Zi's. And that's the sense in which it is a superpotential. Now, this is actually a very elegant story, and it works very well, and it stabilizes the shape. There's a more delicate story, which is started with the KKLT paper, where one also uses D-branes, and that story is a bit more subtle to stabilize in a similar way the size moduli. And again, there's the same story, where I think the criticism that was just mentioned is probably a bit more valid, where the question of stabilizing the size definitely is something that is only under control if the size happens to, if the solution that you find is where the Calabi-Yau happens to be big. If you would, because it's a geometric setting, formalism, And so you make use of that particular approximation. But again, we believe that there are ways of doing this for small Calabi-Yau's as well. Okay. So this is one issue of moduli stabilization. Now, one of the things that, again, I find attractive about the division, which I think I erased between local and global, is the extent to which one is dependent on this arbitrary choice of integer or not. And it turns out that there are many predictions one can make about 40 quantum field theory associated with a given string theory that are relatively independent of this whole story. And so that's where I want to end up today, at least to explain why those things sometimes might be quite decoupled. Okay, let me briefly get this other question out of the way. How to get gauge symmetry. Now, I think it might even be a good guess that we don't even know yet all the possible ways in which in string theory one can get gauge symmetry. Obviously, when I say gauge symmetry, I probably mean non-abelian gauge symmetries. Those are the ones that at least are more characteristic. But roughly speaking, in string theory, it turns out to be the case that whenever you have a situation where you start out with a global symmetry, then if that's a symmetry on the string world sheet, it immediately actually leads to a gauge symmetry. It's one of those things that we can show. In general, the only global symmetry that does not lead to a gauge symmetry is Lorentz symmetry or rotation symmetry. And you can kind of understand that why it doesn't, because it acts non-trivially at spatial infinity. But anything that's an internal symmetry in string theory becomes a gauge symmetry. And this is partly what underlies why the heterotic string has gauge symmetry. So the heterotic string indeed was one way of getting gauge symmetry. Now there are other ways of getting gauge symmetry simply by Kaluza-Klein reduction, but those turn out to be not very practical for a lot of reasons. Now we've discussed also D-branes. And there, again, it's a bit of a miraculous thing if you think about it, that if I take a bunch of D3 branes, if I take a single D-brane somewhere, you can understand why the open string has a massless mode that looks like a photon. If I take another D-brane somewhere else, of course, there's another photon there. And then you can also understand that the strings that stretch between the two indeed become massless when you put them on top of each other. It's still a little bit miraculous that the thing all combines together in a non-abelian gauge field, but it's basically the point that if you have massless charged fields that are adjoints, transform as adjoints, then the only way they can interact is really as a non-abelian gauge field. So stacking D-branes is a good way of doing things. There's another way, actually via singularities, that one can get gauge symmetry as well. And there, the construction is roughly as follows, is that you would have a singularity. This happens in 2A string theory and in M theory, or at least in 2A string and M theory, where suppose that you would have some singular part of your geometry where there are very small 2 cycles. So there are a bunch of small, actually zero size almost, or I would say 0 size 2 cycles. And if you have a 3-form field, which you have in an M theory, a potential, then you can take that 3-form field and integrate that over your 2 cycle, and you get a 1-form field in 4 dimensions, and that 1-form field would be your abelian gauge field. But like in M theory and also in 2A string theory, there's also a 2-dimensional object, a solitonic object, which is the D2 brane, and that can wrap itself over that 2 cycle. Since it actually couples precisely to that 3-form field, it becomes a charged particle in 4 dimensions that couples like a charged particle does to that particular field over here. So membranes, in this case, D2 or M2 branes, they become massless and they are charged here as well. So it turns out that if you take a situation like this where you have a very small part of your geometry and you have 2 cycles, and you let those 2 cycles become very small, and 2 cycles have a certain relationship with respect to each other, they intersect in a particular way, in that way you can engineer a particular gauge symmetry in 4 dimensions. So this is called geometric engineering. So it's at least it's useful to have these things in mind, but as you can see here is that these two things, the d-branes and the singularities, already make use of something that's just localized within the extra dimensions. It's a small feature within the extra dimensional geometry that leads to gauge symmetry. So as I said, I'm only providing a roadmap, so in that respect I'm not going into too much detail here. I may say, we may say more about that when we discuss F-theory later, but things like that. Okay, let's go here. Now, again, briefly again about the global perspective, which is essentially the KK reduction. So suppose that indeed in the heterotic string, and then I'll get back to the global local perspective in a second, that indeed we already have chiral matter in 4 dimensions because that's what the heterotic string gives us. It gives us gauge theories with E8 symmetry. So, so we have both the gauge symmetry, let me call it G or E8, and we have the chiral matter, some psi, and we do the KK reduction, and then we get a 4D gauge symmetry. And we get matter. Now, in the KK reduction, if you start with a gauge theory in 10 dimensions which has E8 symmetry, then you could have a gauge field, let me call it A. So there's a corresponding E8 gauge fields. And on your Calabi-Yau, you could have part of that gauge field turned on. I should say that in the heterotic string, besides having the shape and the size of your Calabi-Yau compactification, the actual solutions of what kind of E8 gauge fields you put on your Calabi-Yau manifold also has a moduli space. So one of the things that you would have to worry about if you do a Calabi-Yau compactification is how do you fix the moduli of the space of solutions of gauge fields, E8 gauge fields on your Calabi-Yau. So that's another thing you would have to worry about. But if you pick a particular solution, then you can take the part of the gauge symmetry that commutes with that solution. So it's the commutant of that gauge field will give me the 4-dimensional gauge group, because that's the part of the gauge group that's unbroken. So that's how you do the Kaluza-Klein reduction. The way in which you get chiral matter in 4 dimensions in this case, what you would do is you would have to look for solutions where since this thing here satisfies the 10-dimensional Dirac equation, and since the 10-dimensional Dirac equation splits into a 4-dimensional plus a 6-dimensional Dirac operator, what you would have to do is you would have to look for solutions to putting the 6-dimensional Dirac operator equal to 0, and the number of those solutions would tell you how many chiral massless fields you're left with in 4 dimensions. So you would have to solve the equation ID / psi is equal to 0, but for a 6-dimensional spinner living on this 6-dimensional Calabi-Yau. And it turns out that the index, or at least the number of solutions that one can get for this thing, is equal to the Euler number of this Calabi-Yau divided by 2, where the Euler number actually turns out to be the difference between those 2 numbers. So the shape of the Calabi-Yau, again, will tell you the global properties of the Calabi-Yau will have some bearing on what spectrum you get in 4 dimensions. So that's why I call this global, But it's a weak form of global in the sense that this is just a number that follows from the geometry. Although, if you now are interested in the Yukawa couplings of these matter fields, those Yukawa couplings would have to come from integrating the wave functions of these zero modes over your Calabi-Yau. Those Yukawa couplings will actually depend on the shape of the Calabi-Yau, and therefore the quantitative properties of the four-dimensional theory are quite sensitive to what the value of these ZIs are. Okay, so let me now give an example of how one can go a bit more to a local perspective via the three branes. Unless there are questions at this point. So let's go to the local perspective. So this is just a simple example. I could take a bunch of the three branes and let me put them on I want to put them on a 6 torus. Now, at that point, immediately I have a problem because the three branes, branes in general, obviously have charge. They carry Riemann charge, and those charge has to be cancelled somewhere. Now, it turns out that what you have to do is you have to introduce, these were mentioned yesterday, O-planes, similarly as in 10 dimensions, and I'll mention that relationship in a second. In order to have the SO32 gauge group in 6 dimension, you need an O9 minus plane. In this case, you need a bunch of O3 planes that essentially amount to an orientifold projection associated with what's called an orientifold projection. Z2 projection on this torus.
So are you putting them in space-time or with
Okay, thank you. So when I say local, I always mean within the extra dimensions. And so since I'm interested in building or engineering four-dimensional field theories, in everything that I'm doing everything space-time filling. So I'll give you the picture. So here's my T6. Obviously it has more sides, but this is the amount that I can draw. And I put my D3s as points in here. So they're points. Here they are. But D3s, of course, have 3 + 1 dimensions, and they fill the remainder of the dimension. So you have to take the direct product with R3, 1. Does that answer your question? So indeed, there is flux that escapes like that, and it has to be absorbed. Now, it turns out that what you have to do in order to get this thing, you start indeed with the type 1 string with SO32, which has 16 D9 branes, and it had this single O9 minus plane, which were canceling each other's charge, and then you do a T-duality. But you do that T-duality 6 times. You do it on all the 6 circles. And when you do that T-duality, it makes the 9 branes into 3 branes. And it turns out that what you have is you get 64 O3 planes. And those 64 O3 planes are all the halfway points on the torus, because what I'm doing, that Z2, it acts like an antipodal transformation on the coordinates of the 6 torus, and that thing has 64 fixed points. And O3 planes have D brane charge minus a quarter, and 64 minus a quarter is minus 16, but I have 16 D3 branes in this particular setting. Yes? Okay. Yeah, there's an SO32 here, and there's a. So let me say a little bit more about this story here, and then we can think about it over here. So the orientifold, since this is an unoriented string, one way of thinking about the 09 plane is that the string world sheet, since it's not oriented, can do something funny. It can become like a Klein bottle. It can do funny things. And you can parameterize those funny things by what's called a cross-cap, where locally the orientation of the world sheet changes. And this cross-cap creates a certain tadpole, or at least it creates a certain contribution to the string world sheet path integral that you would have to cancel from the open boundaries from your D3 branes. And the amount of charge that you get here, indeed, you could say perhaps is 32 or 16. But the way I look at it is that at some level you have to go to the cover, and this is something that we might talk more about later, is that if I think about this as this orientation reversal as a Z2 transformation, then I have 16 D9s maybe here, and then I have 16 D9s here on the other end of the Z2 transformation. So let imagine that the Z2 transformation does this. And then there are open strings that indeed might reconnect with this thing, which would give me an which would give me a U16. However, it turns out that there's a particular requirement on the Chen patent vectors of the open strings that will tell me that although I start out with a U32 theory, which is namely the U16 times the U16, if they are on top of each other, it would be a U32. But I'm projecting out most of that, or at least more than half of that U32, and I'm imposing that everything fits into this SO32. So there's a certain sense in which indeed there are 32 of them, but that's only on a covering space. And the same is true over here, that whenever these 16 D3 branes get very close to one of these orientifold points, then indeed they see their image points. And it's true indeed, if I would take these 16 D3 branes, at a typical location, this would actually be a U16 gauge theory. But if I take them all to sit on top of one of these O3 planes, then it becomes an SO32 gauge theory. Okay. So now, okay, so indeed the good thing about this is that we have these O3 planes that cancel the D3 brane charge, and therefore this is a globally defined solution. One interesting property of this particular thing here is that if the string coupling is not zero, if it's finite, then actually we have to worry about the fact, and this is sort of a positive worry, that those D3 branes actually are heavy objects. This is something we haven't been talking about too much yet, but one of the key revolutions also about what D branes did to our understanding of string theory is that there's the perspective of what a D brane is as a bunch of open strings on a plane, stuck to a plane, but there's a dual perspective that a D brane is actually a solitonic solution. It's a thing that gravitates, it's a thing that moves, and the fact that it can actually influence its surrounding in a very, very non-trivial way led to very deep insights into the relationship between the closed strings and the open strings. And in this particular case, what actually happens is that the back reaction of the D3 branes, so gravity back reaction, is that the D3 branes, they kind of separate themselves out a bit. At least it's one way of drawing it, but it's a bit. This dimension doesn't exist, and it's just in my imagination. But it's still the only way I can draw it. So the three branes will get some kind of geometry around them, and actually if I cluster a bunch of them on top of each other, and I take we take the large n limit where I have a large number of these three branes, this is a very well-known geometry near to the D3 branes, which is ADS5 times S5. And so ADS5 times S5, you can draw it as write it as a metric. The 10-dimensional metric has the important feature that it actually depends that the 4-dimensional part of it has a prefactor, which we call a warp factor, that depends on an internal coordinate. So that coordinate is one of the internal coordinates of my extra dimensions, that coordinate r. And there's some coefficient times r that sits in front of, it's the other way around, I guess, if r goes like that, of the 4-dimensional part of the metric. And then there's the part to the metric that just says the r squared. And then there's an S5, which is the other 5 dimensions. So this together here would be part of my 6 internal dimensions. But another way of saying, looking at the same space, is if I group these 2 coordinates together, these 5 coordinates together, I get an ADS5. And the remainder 5 coordinates is the S5. Now, ADS5 times S5 is a non-compact geometry, and it's non-compact because this coordinate r typically is taken to be from minus infinity to infinity, where taking r to minus infinity would actually correspond to going in that direction. What happens in this particular case is that at some point, this geometry smoothly connects to this T6 geometry that sits here, where I've taken out some ball, some 6 ball, so I have a hole inside of my 6 ball which surrounds these 3 branes, and that region here is replaced by a chunk of ADS5 times that S5. And if you think a little bit about the geometry and topology, you can see that those 2 things can be smoothly connected. So this is a very interesting geometry, which indeed has this important feature that people have played around with a lot, that there's a thing what we call a warp factor. And what this warp factor does, it does something interesting, namely that if I would consider an open string, or no, a closed string, or any object that would live a little bit farther down this region here, where that particular prefactor is very small, smaller than 1. And let me normalize it in a way where if this thing is equal to 1, then I'm roughly over here. So let me call that factor r equals 0, where this thing is equal to 1. That r equals 0 point sits roughly around here. And that's where everything is string size, so Planck scale size. But if I now go to a region where this exponential is very small, and it could be 10 to the minus 15 if this alpha times r can get big enough, then it turns out that the size of the energy, the typical energy associated with a string excitation, is actually not the Planck scale. It's 10 to the minus 15 times the Planck scale. So with warp compactifications, what you can do is you can move around the string scale quite a bit depending on where you are inside of the compactification geometry. So this indeed emphasizes the aspect that I mentioned, that sometimes if you localize within the extra dimensions, funny things can happen. Sometimes all your matter might sit here, and it might have a different energy scale than the one that you would have expected on the basis of your starting point as a string theory. Another important thing, which is the ADS-CFT correspondence, which I should mention, is that which says that the physics on this ADS5 times S5 is equivalent to a particular conformal field theory. So ADS5 string theory, 2B string theory, on that ADS5 times S5 is physically equivalent to a conformal field theory. And in this particular case, it would be n equals 4 Young-Mills theory, SO32, n equals 4 Young-Mills theory, which is the world volume theory that you would have identified as living on these 16 D3 branes. And the claim would be that, okay, you can either describe things using this, or you can describe it using that. And the approximation here would become better if this geometry is sufficiently large. If the size of that S5, which I normalized to 1, which there should be a radius here, let me put it there. r squared gets big enough, and the associated ADS5 has the same curvature radius, and r squared goes like, I think it's 4 pi gs times n, where n is the number of the 3 branes times alpha prime. So if that parameter is big enough, then this closed string description is an interesting dual way of representing the theory on the D3 branes. Now, one thing that this example already makes somewhat clear is that right now the physics that I'm interested in down here is relatively independent and relatively decoupled, if you like, from the physics that takes place down here. I could have done the same thing of putting 16 D3 branes on another Calabi-Yau. In this case, I put it on a T6, but what would have happened if I would have taken another Calabi-Yau? And then the claim would be is actually that locally things still look like this. There are some technical issues in this case having to do with moduli stabilization, brane stabilization itself. But morally speaking, you could say, well, locally things still look like this, and most of the physics that takes place down here doesn't care too much about what takes place down here, whether I took a T6 or something with a completely different shape. And this separates, this is an issue that goes under the name of decoupling, that in principle there's a limit that one could take, which indeed is the limit that Maldacena, for example, took, where you just focus on the physics that takes place down here, and you essentially decompactify the whole geometry. So let's just take this T6 and make the radius of the T6 arbitrarily large. You can take that limit and be left with a 4-dimensional quantum field theory that's living on the D3 branes. At the same time, you take alpha prime to 0, and that 4-dimensional field theory then would be exactly equivalent to that. But the surprising conclusion that Maldacena put forward was that if I take that particular limit, it's not that physics becomes really 10-dimensional. Seemingly, it becomes 10-dimensional. Namely, it lives on this particular space, ADS5 times S5, but it's equivalent to a 4-dimensional quantum field theory. So the very deep fact about this ADS-CFT correspondence is that there's a thing that you could call a decoupling limit, where you focus just on the physics down there. So this is a useful way sometimes of organizing your thinking, where you say, well, if something happens locally in extra dimensions, there might actually be a real sense in which that physics is sufficiently independent of everything else. So at least it separates issues from each other, the moduli stabilization from the matter. Are there more questions about this? Yes?
How about large n limit? I mean, the ADS-CFT correspondence is only valid if there are lots of D3
Now, when you say ADS-CFT correspondence is only valid if there are a large number of D3 branes, the D3, it's not, the correspondence I wouldn't say is only valid then. The correspondence is only a controlled approximation from the supergravity perspective if n is sufficiently large. Not only n is large, the Mills coupling has to be sufficient, the Hopf coupling has to be sufficiently large. Otherwise, you have alpha prime corrections. If n is not too large, then the 1 over n corrections, namely the string interactions, would become important. In this case, the question is 16 or 32 big enough? Let me give you another, a slightly more general setting for the same story. And it turns out that you can have numbers of branes that are much bigger than 32 if you consider more general compactifications. But 32 is still not that small. It's bigger than 3, for example. Yeah, so just again, before I give this general example, so the decoupling limit that I mentioned, what I really mean there is the following, is that if I have a compactification, so I should have the same picture again, where I have the T6 and I have some physics down here, then there's actually a 4D Planck length associated with this particular compactification, because I not only have n equals 4 Yang-Mills that lives on that D3 branes, there's also 4D gravity. And if you just do the Kaluza-Klein reduction starting from your 10-dimensional theory, you find that the 4D Planck length squared is equal to the 10D Planck length, I guess, to the 8th power times the volume of this T6, or in general, the volume of your Calabi-Yau. And what you could do is you could take that volume to infinity, and what that means is that the 4-dimensional theory no longer has gravity in it. Because what has happened is that if I keep the 10-dimensional Planck length fixed, but I take that compactification volume to be very large, the 4-dimensional Planck length goes to infinity, which is like removing that T6, just sending it off to infinity. But I'm left with a theory with infinite Planck length, which is just the pure quantum field theory. So this is, again, what's called a decoupling limit. And the fact that particle physics takes place at a TeV scale, which is much less than the Planck scale, means that this particular decoupling limit should be a pretty good approximation to physics at the TeV scale. Right? If I send the Planck scale off to infinity, TeV scale physics itself might not change that much. Okay. Let me summarize very quickly now a few things about D branes that might be useful. I was about to go and say something more about a generalization of that simple example that I just gave. It turns out that you can do the whole setup with this particular type of geometry in F theory, but I'm going to postpone that particular discussion until next week. Let me make a few comments about D branes. So this is a little bit of an introduction to the lectures that Luis Ibanez will start giving tomorrow. So you can use the 3 branes once you've sort of realized that one can think about things perhaps more locally. So even if you're interested in a string compactification that has 4-dimensional physics, you can actually separate in your thinking a way of getting quantum field theory using branes from the issue of compactification. So imagine that indeed we're looking locally with a bunch of branes, but now the branes are going to do something a bit more interesting than just a bunch of D3 branes. And we could have, for example, in 2B string theory, we could have D7 branes, we could have D5 branes, and we could have D3 branes. Or in 2A string theory, we could have D6 branes, or we could have D4 branes as a way of making more interesting things. And one thing I should mention is that although branes have sort of a more fundamental type, which you could call these D7, D5, and D3s, very often in curved geometries or in generalized constructions, they actually come in bound states. So you can actually have a brane which has somewhat misleading name, fractional branes or magnetized branes, where you would start out with a particular brane, and most conveniently you would start out with the brane with the highest dimension that you want to consider. And then it turns out that that particular brane can have also the quantum numbers of lower dimensional branes. So let me briefly mention that. And you can see that by looking indeed at this action on the D3 branes. And as we were discussing yesterday, it has this Dirac-Born-Infeld action, and it has a Chern-Simons action. And this Chern-Simons term has, as John explained, this particular form. Let me write it like this. F is not the function f I had earlier. It's the two-form, the two-form field strength. It's dA on the worldsheet, or trace of f. Actually, it's just f. The trace sits at front here. Plus the two-form, the NS two-form. And I can expand that thing, and this should be C plus C. Let me do it the same way John did it. Like that. So what you do is you pick the corresponding component of each of these Riemann fields, and you take the wedge product of this two-form here, and you take the sufficient number of wedge products to produce a thing that can be integrated over the p plus one dimensional volume of your D-brane. So the first integral would be just the integral over this Cp plus 1, which tells you that you have a Cp plus 1, that you have a p plus 1 dimensional D-brane. But the fact that a p plus 1 brane also has a coupling to Cp minus 1 is already an indication that there might be a p minus 1 brane charge lurking around here. So there's in particular this coupling Cp minus 1 times the trace of this f plus b, the trace of that curly f. And this integral over here, the integral over that thing, if there's a two-cycle in your internal geometry around which there's a non-trivial flux for that field strength, it actually means that that corresponding brane also carries the p minus 1 brane charge. And more generally, if there is a two-form field present, an NS two-form field present, it automatically means that your brane has some partial charge at the lower dimensional brane. And similarly, if you would go one step further, Cp minus 3 would have trace f wedge f. So, for example, if I start with a 7 brane in 2B string theory, and I would put an instanton charge on it, namely the trace of f2 times f2 is equal to non-zero, then that actually means that there's a D3 brane that also sits on that D7 brane. So in this way, you can do more things. But the really interesting things happen also when you have intersecting branes, because at the intersection of branes, there will be strings, open strings, that connect one D brane with the other brane. And at the intersection is where chiral matter comes. So if you want to do something interesting with branes, you better make sure that you intersect them. So let me briefly give you a schematic way of thinking about this. I'll do that in the last 2 minutes. So I can take a stack of branes, and let me put, say, 3 branes here. And those 3 branes could represent a gauge theory. And if they're on top of each other, then indeed the massless open strings are the gauge bosons of a U3 gauge theory. But now I can take another brane, which on its own would just have a U1 gauge theory, and intersect it with the other one. And what that means is that there's going to be an open string that connects this brane and that brane. Okay? And if you want to know what that open string represents, you would have to quantize what it looks like. And if you do it in flat space, you can do the mode expansion of the open string fields on the worldsheet. And you discover that there are no zero modes for the open string in general. And what do I mean by a zero mode? If I have an open string that attaches to a brane, then it can move along that brane. That's a zero mode. So an open string that would just sit here would indeed have a zero mode that moves around over here. An open string that would sit on that thing would be able to move around. It would have no zero modes if the intersection is a point. And that's an important thing. So when our intersections point, now let me give you two examples. If these are a bunch of these 6 branes, these 6 branes have 3 internal dimensions. And 3 internal dimensions comes from subtracting 3 plus 1 from 6 plus 1, and keep 3 over. And if this is also a D6 brane, which has also 3 internal dimensions, if I take 3-dimensional plane and another 3-dimensional plane, they can intersect at a point. So indeed, these 6 intersecting with these 6 in extra dimensions gives me a point, and therefore intersecting these 6 planes is a very efficient way of making chiral matter. And the reason why it's chiral matter is that if you have no zero modes in your extra dimensions, then there's only one ground state, and it turns out that if this angle is sufficiently tuned, then you have a supersymmetric ground state, which is a chiral field, supersymmetric chiral field in 4 dimensions. But you can even break supersymmetry by having these angles do funny things in this way. In the case of the type 2b strings, it will be the D5 and the D7 strings that you could intersect at a point for the same counting reasons and get chiral matter. So this is an important ingredient, at least when you start building theories with interesting field content. Since my time is up, obviously, again, I wanted to do more, but I'll stop here.